Imagine turning CO2, a major greenhouse gas, into fuel. That is the exciting promise of CO2 hydrogenation, a process that transforms CO2 and green hydrogen into useful chemicals and fuels. One important product is methanol, a versatile chemical used in almost everything, from plastics to fuels. A proprietary technology to convert CO2 and green hydrogen into renewable green methanol is under development at a pilot-scale plant at the University of São Paulo. This is the electrolyzer, the unit responsible for producing hydrogen through water electrolysis. In this process, electrical energy splits water molecules into hydrogen and oxygen. One of the key advantages of this technology is that the electricity used can come from renewable sources, such as solar or wind power, making the hydrogen production process clean and sustainable. The hydrogen generated here will later react with carbon dioxide to form methanol. Here is the CO2 storage tank, containing the captured carbon dioxide feedstock. A principal and key aspect of our product is the capture of this CO2, effectively preventing it from entering the atmosphere. This CO2 can be captured from multiple sources, including industrial emissions and, importantly for this project, CO2 produced during biogenic processes, like the fermentation of sugarcane from ethanol production in Brazil. This is the compression unit, where the carbon dioxide and hydrogen mixture is pressurized before entering the reactor. Inside this module, a gas compressor increases the pressure to the levels required by the process. Applying high pressure and high temperature is a key strategy for this reaction. These conditions are crucial because they favor the formation of methanol by driving the reaction forward and increasing its rate, while also being essential for the catalyst to function effectively. Adjacent to the main process, you will find our mini pilot plant. This unit is designed for a more flexible testing and scaling studies. It replicates the core process steps on a reduced scale: gas compression, catalytic reaction, and gas-liquid separation. This mini plant is utilized mainly for crucial research, including kinetic studies to understand reaction rates, advancements in catalysis to improve catalyst performance, and overall process optimization. For detailed process understanding, it features an integrated gas chromatograph for precise online composition analysis. The system is managed through a comprehensive computer control interface, enabling precise parameters adjustments. This mini plant is mainly for R&D purposes and does not incorporate the distillation unit seen in the larger plant. Here are the catalytic reactors, the central components of our plant. Inside, the CO2 and hydrogen gases undergo a chemical transformation on the surface of specialized catalysts, producing methanol. These catalysts are key components of our project, having been developed explicitly for the CO2 to methanol conversion. Since the reaction requires high temperatures, the reactors have an integrated heating system that maintains the catalyst bed at the optimal operating temperature. Together with the high pressure provided by the compression unit, this setup ensures that the reaction environment meets the conditions for methanol synthesis. After exiting the reactors, the mixture enters the gas-liquid separator. Here, the temperature and pressure of the process stream are considerably reduced. These decreasing conditions allow the methanol and any produced water to condense into a liquid phase, while the unreacted CO2 and hydrogen remain as gases. The fluid stream containing methanol and water is then sent to further purification, and the unreacted gases are recycled back into the process to maximize conversion. Following the gas-liquid separation, the crude liquid methanol is fed into the distillation column. This unit separates the methanol from water and any remaining impurities. The result is a highly pure methanol, typically with a purity above 99%. This product is then ready for diverse uses, including as a fuel component for direct use in internal combustion engines, such as in marine vessels and vehicles, as well as in processes like MTO, methanol to olefins, and MTH, methanol to hydrocarbons. It is also a key building block in the production of formaldehyde, acetic acid, methyl third butyl ether, MTBE, dimethyl ether, DME, and a wide range of other chemicals like silicones, urethanes, and pharmaceuticals. Furthermore, it serves as a valuable solvent in many industrial processes.